Thank you very much for such a kind introduction. And I'm very happy to be here for this as a speaker of this Asian Winter School, which is a very nice tradition. Which also I gave several lectures before, and I really enjoyed it so much. And also I'm really grateful to wonderful organizers of this conference and of this school, especially Wei-son. Thank you very much for invitation. And in this lecture, I'd like to give us some basic introduction to the subject of quantum entanglement and holography, ADS-CFT. And also, in the end, I'd like to also mention some recent problem of this black hole information paradox, which I think it's hopefully complement to Henry Maxwell's talk. And so here are my plan of my lectures. And so today I'm mainly focused on basic aspects, especially this basics of, first time, let me begin with this definition of quantum entanglement and basic properties and entanglement entropy and basic properties of that. And then I go to entanglement entropy in quantum field theory, especially conformal field theory, CFTs. And finally, probably I will talk on this holographic calculation of entanglement entropy, holographic entanglement entropy. Probably these are today's topic. And tomorrow, I'm going to talk about more recent development, starting with this entanglement wedge, idea of entanglement wedges, and bulk reconstruction. And I would also like to discuss quite a bit about the computation of entanglement entropy in the presence of boundaries, which is called boundary conformal field theory. So usually we have conformal field theory, but with some boundary. And this is also have a nice application to black hole information problems these days. So I would like to explain a little bit on that. And I end up with our recent work on this calculation derivation page curve by using a setup called moving mirror by using ADS-CFT correspondence. Okay, so yeah, here I'm going to write this lecture contents. So let me start with this basics of this quantum entanglement. So anyway, I will post my better writing notes later on the maybe on this Slack. So first, I'm going to very elementary thing. I think probably many of you are very familiar with this, but I'm just talk about quantum mechanics, but this is very important concept. So what I'd like to talk about the difference between pure state and mixed state. As you know, so let me start with pure state. As you know, this is just usually state in quantum mechanics is given by specifying particular wave function. Or we can write some state, right? Psi state. And this is we think this is a kind of definite state. This is a starting point. And usually textbook of quantum mechanics start from this. And if you talk about some spin system, like one qubit system, we write it 0 to be up spin, like 1 to be down spin. These are called, so this linear combination we can consider in quantum mechanics. This is called qubit, right? This is qubit, quantum qubit. This is one qubit. If we have two of these spins, then you put 2 qubits. This is a kind of bit, a quantum version of bit, of basic unit of information. And this is a pure state, right? You have a linear combination state, but this is anyway, even though you take a linear combination, and that we say this is, 0 appears probability alpha square, right? 1 appears beta square. This is anyway, this is a quite definite state in quantum mechanics. But on the other hand, there are some idea of this mixed state, right? This is given by superposition of this pure state. This is, I can just write it explicitly. So this is written by this using density matrix, and some sum of some state, and this is a pure state. Like psi, let's assume we have several of these psi, pure state, and some a kind of superposition. And this is a density matrix. And the idea of density matrix is just probability distribution, right? So total probability is just one. And let's assume these are normalized. These are normalized to be, maybe we can just diagonalize it. Then one. Then, so this means, of course, this means that sum of pi are equal to one. This is a probability. This is probability. So we have many pure states, definite state labeled by I. And so each I, the psi I is realized with a probability pi. This is a mixed state. In general, this kind of superposition is a mixed state. And this is an ambiguous state. There's a lot of ambiguity because of probability distribution. Right? This is definite state, but these are ambiguous states. And if we want to calculate some expectation value of some operator, so we just take a operator as a sum operator. We take a just trace O rho. Rho is this distribution, probability distribution. Right? We just take a weight over this probability distribution. So this is a mixed state. We should always distinguish two guys: this pure state and a mixed state. And usually good theory of quantum entanglement usually formulate for pure states. But in the end, we have to generalize to mixed state in some cases. But my talk is mainly, I'm focusing on this pure state because this is the most basic target of the quantum states, and it's much easier to formulate theory of quantum entanglement. But if we want a more advanced story, we can generalize the story to mixed state, which is more complicated. Okay, so these are just, I'm talking about very elementary thing, mixed state and pure state. And let me go to quantum entanglement. So now I go to explain what's the quantum entanglement. Sometimes I just write it QE for simplicity. And to consider quantum entanglement, we always start from bipartite system. Consider bipartite system, quantum system, which means that Hilbert space is factorized into two parts. Right? Simplest example is 2 qubits. If we have 2 spins, you can decompose Hilbert space into 2. But you can think about many spins, but you can just call part of the spins A, and the other part is called A, B. Then you can have this bipartite system. So anyway, so I usually in quantum information theory, we just write that AB means just A union B. So we also follow this notation. And a pure state. So now I'm talking about pure state. Pure state psi as quantum entanglement. Quantum entanglement. This is if and only if this psi cannot be written in a direct product form, right? So this is AB, right? Hilbert space AB. This means just some existence of some state which so that psi state is factorized as a direct product, the direct product. So this is a definition of quantum entanglement. If a state can be factorized as a direct product state, that means we say there are no quantum entanglement at all. But if we cannot factorize that way, then we can say there are some entanglement, some quantum correlation. And basically, this means some quantum correlation, but very ambiguous one. Quantum correlation is very ambiguous. But anyway, but quantum entanglement is more definite concept because we can define this way. And this is a pure state, right? This is the quantum entanglement for pure state is easily formulated like this way. But maybe you are wondering what about mixed state? I just write it here. For mixed state, So we say rho AB has quantum entanglement when, if and only if this rho AB is something called separable. Separable. I should explain the meaning of separable, right? Separable. Separable means density matrix rho AB is decomposed into this way, right? Some probability distribution of factorized state, like this. Not just direct product state. This is a more relaxed condition than this direct product state. Pi is some classical and some just number, right? Positive number, probability distribution, so that total sum is 1. And point is that these two states are factorized this way. So this is called separable state. And that case, there are some correlation, right? There is a correlation which is related to this Pi, but this is classical correlation. And we say this is nothing quantum, right? Because we can realize this in classical way. Just classical probability distribution looks like this. So that case, anyway, there are no entanglement at all. So, sorry, this is very should not, it's not this is not separable, of course. So if rho A has a quantum entanglement, it's not separable. If it's separable, there are no quantum entanglement at all. So this is a definition of mixed state. And now I go to examples. So let's simplest example is always 2-qubit system. So the first one is a trivial example, just direct product state, which is like 0 plus 1. And for example, this is just example. We can take a linear combination for A spin and B spin. There are 2 spins, A spin and B spin. So these are 2-qubit system. But anyway, these are just direct product. In that case, there are no correlation at all. No entanglement, no quantum entanglement in this case. Okay, and the non-trivial example is like this. This is some typical example, the EPR state or Bell state. So this is the EPR, Einstein-Podolsky-Rosen state, or sometimes called Bell state. So this is just defined by like this, 0, 0, AB plus 1, 1. So they are actually entangled. These two guys are entangled. So you can think this because actually this is maximally entangled. So you can think this is maximally entangled because you can imagine we measure one of the spin A, right? Let's assume there are 2 possibilities, 0 or 1. Right? We are not sure which one, 50%, 50% realized, right? But anyway, if you find first spin is 0 or just up, then immediately we know that second spin, B spin, is also up, right? These two guys are correlated. If A spins down, then B spins down, right? There are very strong correlation between the consequence of measurement. So in that case, we say it's quite entangled state. And so this is a quite important state, actually maximally entangled state. Now this is kind of basic unit. It's qubit of quantum entanglement. This plays a very important role later. This is a unit. This is a basic unit. Basic unit of quantum entanglement. Later we want to measure, right? We want some measures the amount of quantum entanglement, which is called entanglement entropy. In that case, this is a kind of basic unit. How many EPR pairs are there? Basically, entanglement entropy, as we will explain, measures the number of these pair pairs or EPR pairs. So these two guys are, strongly entangled, right? A, B, these two are entangled. But this direct product is just separated, right? Just independent. Okay, and I think this is a basic point. And so now I go to entanglement entropy. Right? So this is a quite abstract way. We have definite, definition of this, quantum entanglement, but we want to quantize, right? We want some quantity, right? So this is the entanglement. I often write it just EE for simplicity. And let me start with entanglement entropy. Entanglement entropy. So this is so we talk about some particular states that, so we have some, sorry, we start with some pure state, or let's assume always pure state, because entanglement is much easier with pure state. And in this vector in Hilbert space, total Hilbert space, which is factorized into two parts, right? Bipartite system, as we already seen before. And then we introduce something called reduced density matrix, rho A, by taking trace over B. So this is a state for A. Right? This is a mixed state, and this is called reduced density matrix. Reduced matrix. Okay, and then we can define entanglement entropy. We can define entanglement entropy as a von Neumann entropy, trace rho log rho. Okay. So this is a definition of entanglement entropy. And but practically, it is easier to calculate some one parameter family of this entropy called linear entropy. So that's I'd like to define linear entropy. Linear entropy, linear entanglement entropy. This is defined as A with some particular parameter n and 1 over n log trace rho A to the nth power, right? And if we take particular limit, n equal 1 limit, then we recover just standard von Neumann entropy, entanglement entropy. And the n is usually some integer, some 1, 2, 3, like integer, because to that we can have some just nice power, but we can, in the end, often we can analytically continue to a real value n, and that is quite useful. And by using that analytical continuation, you can define n equal 1 limit. Right? So this is a way to consider entanglement. So I'll explain how we can calculate it. This is von Neumann entropy. Okay, so then, but before I go on, I would like to explain basic properties of entanglement entropy, and later I will give some more intuitive understanding, more precise definition of entanglement entropy quantum information theory using Bell pairs. But here, this is a very particular physics or high energy friendly definition of entanglement entropy. We can define just a quantity by density matrix, just equation, right? And but once you define this entanglement entropy, so you can have nice properties of entanglement entropy. So it's here. So first property is yeah, this is something we explain later. For pure state, this is very basic properties. This is actually motivation why we consider entanglement. For pure state, point is not mixed state. Entanglement entropy measures the amount of entanglement. QE. This I will explain it. And so for the simple equation, we have a very basic property for pure state. Of course, this is a pure state. Psi AB is pure. For pure state, SA equals SB. Of course, this is positive, non-negative. And this means that if you can think some A is very large, right, and B is very small, right? But you can replace this with B, and you can just replace naming, right? The big one is B and the small one is A, and still entropy is both the same, right? That means entropy is not proportional to size of the system, right? Size of the subsystem. So this case, this means that not this entanglement entropy is not extensive, right? As opposed to thermodynamic entropy, thermal entropy, it's different. But you can, if you extend definition of entanglement entropy, right? So we started pure state, but if you just pretend the state, pretend that some mixed state can be also, we can use mixed state to define entropy, then you get thermodynamic entropy. And that case is, we have extensive property. So this is only true. So this equality is, this equality is only true. This equality is only true for pure state. Only true for pure state. And number 3, and when this is when HA, we talk about this 3-partite system. Let's assume this total system is 3-partite. Then we have some basic inequality, right, called strong subjectivity. This is a very basic inequality. SAB plus SBC is greater than SABC plus SB. Right? Here, of course, I mean A union B. Already I used this. So this is called strong subjectivity. Strong subjectivity. This also I will explain this by using holography later. But to derive this formula itself is quite a little bit tough. A lot of calculation. You can look at this, basic textbook, many different. Or for example, Nielsen Chan textbook. You can find some proof. But actually, we can understand this inequality in very simple way. You are using ADS-CFT. That also I will explain later. And finally, there are one more property. It's called concavity. Concave is concave function. Entropy is always we say it's concave function. Concave is like this. Right? Of course, convex is opposite. The convex is opposite. Always we say entropy is convex, concave. So this is written this following equation: Pi S rho I. Rho is just the density matrix. There are some series of density matrix. And the and the PI is a probability, right? Probability distribution. Of course, it's like PI. Sum of PI is 1, and PI itself is always positive, right? Okay, and so the point is that this is actually this combination. Sum is always, because of concavity, it's like this, right? Okay, here it's like, you can think this rho 1 and this rho 2, right? But here it's like this rho 1 plus rho 2 over 2, right? So it's like this, but we also have some upper bound, right? This is sometimes useful, and this is like this. Upper bound is given by the same one, but with some extra term, right? Log pi, log pi. This pi log pi is called Shannon entropy. a classical version of quantum entropy. Shannon entropy. So this is it's good because we have an upper bound and lower bound, right? So we can prove this precisely. I'm not doing this, but if you are interested, you can look at textbook. But this actually, so I'm not, so anyway, I will not have time to talk about this later, but this in the context of holography, actually this is quite useful. So if we think about, this is a little bit advanced, but if we talk about some, two density matrix, rho 1 and rho 2, right? And have some, each has some classical gravity dual, some geometry. Geometry number 1 and geometry number 2 by using ASFT. And then we can think about this kind of mixture, right? P1, rho 1, P2, rho 2. And that's case how entanglement entropy can be computed, right? So actually, so if we calculate this entanglement entropy for this, like this, sorry. S is like P1, rho 1 plus P2, rho 2, right? Actually, we can say this is just linearly approximate. This is something we can learn from this formula. Because this guy, this case is we have some contribution here, it's very, very small. Because entropy, entanglement entropy in large N theory, in the holograph theory, it's very, very large, in order central charge, or N square. Then itself, it looks like N square, order N square. So this guy is just order 1. So that way, we can use this upper bound, lower bound, that we have some linear approximation. And this is called linearity. Linearity of this holographic entanglement entropy. So you can just superpose state, and it's much like calculation looks like linear. But of course, if we talk about, if we sum over many, infinitely many states, then you get this term is very, very large, right? It can be compatible, compared with N square. In that case, we cannot say any linearity. Okay, yeah, this is a introduction, but I go back to this elementary example again. So this example to qubit system. And so we can talk about some state, more general state, cosine theta. I will also use this state later, so it's good to preparation of this later argument. 1, 1. Sometimes this means, of course, this guy means just 0A times 0B, right? The same as 1, 1 state. So that case, we can let's compute this, reduced density matrix just following this AB, right? Definition, and you can square of this, and so you get the cosine theta square 0, 0, right? Or sine theta square and 1, 1. Right? Very, very element. And then it is very not easy to calculate nth order of linear entropy, which is like 1 minus n and log plus rho a to the nth, right? And then 1 minus n in log, it's like cosine theta to n and sine theta to n, right? And you can especially take the limit, n goes to 1 limit on Neumann entropy, or just you can take a rho log rho directly. So then it's like this is a rho, this log rho, right? And we have another contribution of rho log rho. And of course you can, if you plot this, about function of theta, maybe, yeah, maybe not theta. I think it's good to just write it. Cosine theta, right? Maximally 1, right? And this is 0. And if these two guys are same, right, that means square root of 2, right? Square root of 2 over 1. And this entropy follows like, if theta is 0, obviously this is 0, right? This goes to 1, this goes to 0. So it's always, so that means it's like this. And the maximum value is here, and this maximum value is log 2, right? Log 2 is both are half contribution. Right, log 2, because there are 2 degree of freedom, up spin, down spin. So log of this micro state number is gives entropy. So this is a, of course, basic example, and we would like to promote this to quantum field theory later. But before I go on, let me explain the more heuristical meaning of entanglement entropy. So this is this section. This is operational meaning of entanglement. Okay. So so first of all, what I would like to explain here is the following claim. Claim is like this. So entanglement entropy is actually counting number of EPR pairs. Pairs between A and B. Again, we assume pure state, right? We assume some pure state. Sorry, we assume some pure state, and we would like to measure entanglement. So you can write some picture, right? So we have A system, and B is just black dot. And we have some originally, in general, you can imagine some middle value of theta here, for example. So then it's very complicated, entangled very complicated way, right? Sometimes this spin maybe also entangled with this guy, and this spin is just this guy, but this guy is maxed with, also this guy is also entangled with, and so on, right? This guy may be here and here and here, right? It's very complicated, entangled in general, complicated way. But we can simplify the situation by some nice procedure, which is called, I'll later explain a bit, it's called LOCC. Then, so you will have the same system, right? We have the same system, AB, right? But in the end, after do this, then we have just beautiful pairs of EPR, their pairs. We get just some number of EPR pairs, and then we can talk about. But of course, there are many different ways to do this, and we have to maximize the number which we can extract. So maximal number of EPR pairs, which we can distill from, extract from this original system. And this is actually coincides with the entanglement entropy. But this is a little bit rough statement. I will make this more precise. But this is what we want to do. But also I should explain what is the LOCC, right? LOCC, and maybe I did it here. LOCC is local. LO is local operation, and CC is classical communication. And local operation is something very quantum operation. So you can act some operation. So maybe I agree. So we have some only. So let's assume A and B are actually far apart. Maybe A is in Beijing and B is maybe in Tokyo. So they are separated, and they are quite a different. They are separated to experimental laboratory. They are laboratory. Let's assume A is laboratory, B is laboratory, right? And we can do some in laboratory. You can make some very sophisticated quantum operation right here. It's some unitary transformation between these two spins or these spins, or some projection measurement, some measurement you can do. Right? B also independently you can do the same thing for B. Right? You can act some unitary operation. But because A and B are far apart, we cannot act any quantum operation which also mixes A and B, right? And between A and B, we can just only send emails or making phone calls and so on, maybe sending fax and so on, right? And then that means we can hold separated laboratory. We can just do some classical communication. classical communication is just sending, classical bits, like sending email and so on. So by only that, using that kind of procedure operation, so it looks like we cannot change the entanglement between A and B, right? So to create an entanglement, we have to act unitary operation, right, which mix A and B. So actually, we can say, actually more precisely, we say such an operation, LOCC operation, always decrease entanglement. Sometimes it will break some entanglement, but we cannot create entanglement. And this is a quite nice operation, and also very formulated in this very mathematical way, as I mentioned. So just using this LOCC as a rule, right? And using LOCC, and we try to, reorganize entanglement, and so that we pick up some very simple pairs of EPR, pair pairs or EPR pairs. So that's the rule. And then, of course, we can there are many different choices of LOCC, and we have to maximize, right? We have to maximize the number of EPR pairs we extract. So this is actually what we want to do, and LOCC is like this. And but more precisely, following statement, we should use more. We need to take something called asymptotic limit. This is, quantum information theory people always do this to make quantities very smooth. So that means what does this mean? So we have some state like pure state AB, but the point is that we have to take some copy of this guy, right? So let's call this is like M, right? And then we act some LOCC, and in the end we extract some EPR pairs. Okay? EPR pairs, some number, right? Okay, some number N, right? But of course there are some contamination, some extra guys, right? Some of them, some of this entanglement here is replaced with EPR pairs, but other guys are not entangled, so just some kind of trash is remaining. So this, let's assume that we did this, then, and we have to maximize over this, N. But anyways, this theorem, basic theorem, tells us that this entanglement entropy, is actually equal to. So the point is that we prepare some copy or multiple copy of the original system, right? And this makes a calculation continuous. So we have some N, but of course we have to maximize it, right? There are many different LOCC. We just pick up best one and divided by, we take average number of EPR pairs, because we are only interested in entanglement for each of this state, not M copy. So we have to divide by N. And then, then you can show that, but there are some small deviation which just come from basis of this logarithm, right? So this, I'm talking about the EPR pair and one qubit like 0 and 1, right? Two states, but we usually use E, right, for logarithm, base of logarithm. And so the point is that, anyway, it is clear, right? So from this definition, it is clear this measures amount of quantum entanglement, right? Because how many EPR pairs we can extract. So the question is how many EPR pairs can be distilled, extracted. Often people call it distilled. This is a question, right? And this is, we can measure this amount by using entanglement. So this, I will give some explanation, some kind of derivation of this formula. Okay, so anyway, this is one of the basic things I wanted to talk in this section. So let me give some explanation. So actually, this gives some basic derivation of this. Original proof also like this. And so, but yeah, we just take a start of the 2-qubit state because it's easier. This psi AB is 2-qubit, but this is actually quite general. You can rewrite n-qubit state in terms of 2-qubit state, taking limit. Let's take. So this, here I go back to the previous example, right? Psi AB, I write it cosine 0, 0, right? But I just write a C, right? For simplicity, I just write it 1, 1, AB, same as previous one. And C is cosine theta, S is sine theta, right? This is a very basic state. And so if you talk about, if you have in mind this procedure, right, we are literally to get in trouble, right? Because it's a very ambiguous state, right? As a very generic coefficient, how many pairs? Probably 0, right? It's not possible to get, because if we take this square root of 2, square root of 2, then we get just only 1 bit of 1 EPR pairs, right? We get. But if this is not square root of 2, then we cannot get any pairs. So this looks like problem. But here, this multiplication of M copy plays asymptotic limit plays a very important role. So let's take. So we take this guy M copy of this, then we can expand, just using binomial expand. So we, we just talk about this M copy, right? And leading terms like we start with C to the M, we can just M copy of this, then point at 0, 0, 0, 0, right? 0, 0, 0, 0. So here we have M zeros and M zeros. M is here, right? And this is still let's call this AB, right? Let's expand it, but it's AB. And so we just N copy, and let's assume only one of this guy comes, and the M minus 1 here, right? And the 1 is here. Then Cm minus 1 to the S. Sorry, let me not write it here. Okay, plus Cm minus 1 S. In that case, there are several possibilities. Maybe first one is 1, other is 0, like this, right? And also maybe first one is 0, but next one is 1, like this. And many other, right? So again, this is M qubits, M qubits, M qubits, M qubits. I just we take a binomial expansion, right? And anyway, we have this something like this, and yeah, so there are here it's like M terms, right? Because the 1 is here and the 1 is now second position and so on. But you can have a more complicated guy. Next one is a little bit complicated, right? Because there are 2 1s, right? 1 1 0 0 0 1 1 0 0 0 0 0. Plus, 1 can be maybe here also, maybe 1 is like this, right? I cannot write, especially. You can imagine that case, there are many terms, but there are C combination, right? C is combination, M2, like, of course, M minus 1, states, right? Terms appears, right? We can do the same thing, until end of, like this. And finally, so, okay, so finally, what we end up with, we can rewrite this in this way. So we introduce K. K is like this. This is, we call this as K equal 1. K equals 0. This guy is K equal 1. This is K equal 2, like this way. Combine this. Then, M minus K, SK. And we take I from I to CMK. That's because there are, CMN terms like this way. CMK terms. And so here is a projector, right? So this projector is defined A part, same state actually. Same state because you can see this state and this state same, right? This is state same because it's originally they are combined in the same way. The state same. So we decompose this. So yeah, more just to remind. So this example and K equals 0 and the P 0 is only the one state, right? Only pi takes 1, this is 0, 0, 0, 0, 0. This m spins. K equal 1, k equal 1 corresponds to this guy. This guy is P1, k equal 1 case, you have a 1, but there are many. 1 is like 1, 0, 0. 1, 0, 0, 0, 0. But 2 is a little shifted. And then end up with, PM1, which is like 0, 0, 0, 0, 0, like this, M state, right? So we have this project. We can rewrite this. Now, by using this, explanation, so let me write it again, psi AB times n, right? This is asymptotic limit. Yes. Okay. So anyway, we want to work with this, this state. Then what we would like to do is the following. So we take interpret this state. We imagine, we make a projection. You can do some, projection, like LOCCs, LO part of LOCC. And so that we extract particular state, we can just act projection in a laboratory. We pick up this guy. Right? So then this is like projection. This is like a projection. Projection, which is like pi k. Right? Pi k given by this just PIK. PIK. This is a projection. If we do that, if we restrict to k sector, particular k sector, then what we get is some probability pk is given by this coefficient, c to m minus k, s to k, but square, right? Because it's and times c, because there are number of terms, right? Like this. Of course, you can confirm, sum over pk, k equal 0 to m equal 1, right? This is just binomial formula. And yeah, okay, so this is we get a probability distribution. So we can restrict k sector given by this EPR pair, right? With this probability. And then you can talk about averaged number of EPR pairs. You can calculate average number of EPR pairs. This is maximal number basically. Is given by putting weight, this pk is this one, right? With weight and there are possibility. But for once you specify particular k, right, you get this maximally entangled state, right? Then we know entropy, right? For maximally entangled state, we just take a log of the number of state, right? This log of c, m k. This number of states, just number of this state, c m k. And yeah, so here actually this is the answer, but we can little go more. So because we can take some limit, right? We take a asymptotic limit that m goes to infinity, right? So you can remember, right? So you please remember this formula, we take m goes to infinity. So we goes to n goes to infinity, then we can do some saddle point approximation. I'm not going to do this. Right? This is kind of exercise, so you can do this because it's a 2, like log 2, like there are some extra factor here, and this is some factor, and this c square, and you can just do this saddle point approximation, and precisely then we get what we expect, like this. This is here, it's like saddle point approximation. this kind of exercise. Right? And then, so that means, right? So we take n max over m, and m goes to infinity. Right? We get is like this. Indeed, this is entanglement entropy, right? So entanglement entropy times log 2e. Right? This is something we already argued, and indeed we can derive this relation between entanglement entropy and number of EPR pairs this way. This is quite a basic theorem in quantum information. Okay, so yeah, so here I just finished my explanation of basics of this quantum entanglement. And if you have a question, maybe it's good time to ask. Any question? Okay, but anyway, you can ask also on the Slack. Yeah, yes.
Maybe you talk later, but do you have any holographic interpretation of these procedures?
That's a good question. Yeah, actually, to be honest, I don't have a good idea. But maybe some interpretation using tensor network description of area safety gives some hint of that, because tensor network procedure extracts some amount of entanglement. But I think that's a very interesting question. Actually, that's the reason I talked also on this. This is issue, a precise connection of this procedure, especially for this asymptotic limit. Asymptotic limit, meaning of asymptotic limit in area safety is not clear at this point. I think it's quite interesting for future works.
Is this asymptotic limit can be viewed as a continuous limit in lattice quantum field theory?
Lattice quantum field theory. This is asymptotic limit is, I think, flow related large n limit of gauge theory. In some sense, my feeling is that if we talk about area safety, it looks like already we took asymptotic limit. As if we don't need, it seems we don't need asymptotic limit. Yeah, so because of the structure of Hilbert space is kind of large n and many binding sector in the case of area3 CFT2, so somehow that helps us to, the situation is improved, right? So that we don't need to take asymptotic limit more. But I'm not sure. Yeah, that's a good point, and I think it's quite interesting future direction.
Thank you.
I saw some question in the chat.
Yes. I see. Yeah.
But I don't know.
Okay. Yeah, I think this is about the replica. I think this question is about limit. It is true. So I think the question is like, what is here? Yeah, here, entanglement entropy. So I said that we calculate linear entropy for any n, and we take analytical continuation about n and get entanglement entropy. But of course, for that we need a asymptotic condition. So this the dependence of n should be somehow smooth, and have a nice asymptotic behavior when n goes to, for example, infinity also. It is true. So yeah, there are some mathematical theorem for which precisely make some statement. So that's of course, and indeed we sometimes we have phase transition depending on value of n. So at n equal 2 or some n, there are some also such example. So this analytical quotation is very tricky, I should say. Okay. If not, no more questions, so I will go to more high energy theory calculations and properties. So, okay. So now I'd like to talk about this entanglement entropy in conformal field series. I'll just give basic summary of the properties of entanglement entropy in conformal field series. But yeah, so related to this also previous issue. I should explain how to calculate entanglement entropy in general in quantum field theory. This is basically I'm going to explain replicatory. But before that, I only talk about two qubit systems. So we should think about entanglement entropy in quantum many-mode system. This is, for example, we often condensed matter literature. We often think about spin system. We can also think about fermion system or boson system. But I just write the spin system picture. So we have many spins. Right? This blue points are spins. There are many spins. And to define entanglement entropy, you need to specify this decomposition, right? Hilbert space. Point that H total Hilbert space always decomposes into two parts, HAB and HB. Right? And we can just particularly choose anything you like, but you can call this 4 points region A, and the other guy is B. Maybe outside is B. Then, of course, we can realize this decomposition. Anyway, and so we often write it this cutoff, that is constant, that is spacing to be epsilon. This distance between spins basically, and we take because of so many infinitely many spins, we can regard this epsilon goes to the, we have some epsilon goes to zero limit. Okay, we go to epsilon goes to zero limit. This is called continuum limit. So that we have nice Hamiltonian, we get a nice quantum field theory. And yeah, okay. Okay, so and then we have some system. Sorry, we have some system. And some region is A. Okay? Some region is A. This is region A, and outside is B. Okay? So this is now we are in the quantum field theory, QFT. Right? And then we can decompose. So here in the limit, using this regularization, we can decompose Hilbert space like this. But of course, we have to be careful about the boundary condition at this entanglement boundary. But under proper boundary condition, we can calculate this quantity. And so anyway, so this way, you can have some definition of entanglement entropy. So that way we can define entanglement entropy in quantum field. Of course, it's like entropy is again rho log rho, rho A log rho. This is a definition, but then this is very abstract, so we should say how we can calculate. Then here, the basic approach is called replica calculation. And we just use path integral. We use Euclidean path integral. We use Euclidean formulation. In that case, so we have like we have path integral like this and like this. So here, what I mean is we have path integral from tau equal minus infinity. This tau is a Euclidean time. Tau is Euclidean time. Always in my talk, it's like Euclidean time. And tau equals 0. So we have path integral. Right? We have path integral from minus infinity to tau equals 0. And then we read off wave functional here. So this defines some state, which we write it. This is we define precise state, right? And on the other hand, we have like path integral, we tau equal plus infinity to tau equals 0. maybe we can go this way. And then we can read off some wave functional here. Because this is an infinitely long path integral, it's much like exponential beta h and limit, beta goes to infinity, right? So that case, we don't need to worry about the boundary condition here, right? It's just completely dumped down to ground state. I'm talking about ground state calculation. So that case, we get this is equal to, we have Bura and Ket state, right? And if we, take out, if you, identify this with this, then we get the inner product, right? But we don't want inner product. We want a reduced density matrix. What we want is rho A to some, some alpha beta. It is reduced density matrix we want. So this case, we can again do some path integral. Okay, sorry. We have path integral, and we put some cut here, like this. Then we have like alpha and beta. This boundary condition is the argument, of matrix here. And so this is a subsystem A also. So okay, so write it A is here, and this guy is A. And this here it's A. This guy is A. And we have like other region. Extra guy is B. Right? A is here. A is this interval. And yeah, so and we take already inner product for B, right? And so we glue this point, this line, this line. So that means we are already trace, right? B is trace out. What I mean is that we already B is trace out. This guy. And then, so we have some open boundary, and the boundary condition beta and alpha is argument of this reduced density matrix. And that way we can calculate, so finally we calculate trace, right? So we wanna trace to rho A to nth power. This is, element of basic quantity which we need to calculate linear entropy. So we have, actually n copy of this guy. We have n copy of this guy. I just only write it 4. But basic idea is we prepare this guy, So we prepare this guy. Just quickly write it here. We prepare this guy, right? We should prepare this guy, and we paste to each other. This line is with this line, and this line with this another one, and finally this line goes to upper line, right? And we glue this to each other because this is a trace. How, what trace do? And then after that, we get this cut here, and we have cut here, and they're connected. Like you go around this cut, then it goes to down, and if you go around, then goes to down, like this way. So this is something called n-sheeted Riemann surface. Riemann surface, right? Which we write it. I write it sigma n. N is this n seats. There are n seats. Okay, n seats. There are n seats. Here. So first one is 1, 2, 3, and 4 n. Okay. So anyway, in the path integral way, so we can prepare Brand Ket state, and we take a trace law to the n's like this way, and just a kind of n-seated partition function on n-seated Riemann surface. So this is a replica. Okay, and in this way, so what we learned is like this. In this way, what we learn, trace law to the nth, but we have to be more precise because because law trace of law is I mean 1, right? Normalized 1, but obviously this is not normalized this way. It's actually partition function. Partition function is not 0 and not 1. So that means we have more precisely should write this way because we have to divide normalization, right? If we talk about, you can talk about trace of this guy should be 1, right? But it's if we trace means just we paste to each other, but this becomes kind of partition function, which we write it to z1, right? Only one seat that we just write z1. z1 is not 1, so we have to divide. Actually, we have to divide like this way. So yeah, I should write it this way. So we have to divide by z1, right? And also here also you need to minus to the n. So this is exactly this one. And yeah, and the n equal to partition function on sigma. Sigma n is precisely this. Sigma n. This is a precise way to calculate this trace law to the nth. But then once you find this, then you get a linear entanglement entropy. Linear entropy. Linear entropy. You can get linear entropy trace law A nth because it's 1 minus n log trace law A to the nth. Okay. So this is how we calculate entanglement entropy, but we can actually have one more different, more useful description, which is directly related to this one. So here is that. So we can remember the previous calculation. Okay. So maybe I just let me move some part here. Okay. And what I wanted to say is, yeah, we have some this n seat, right? We have n seats. We have in seats, maybe 1, 2, 3, and blah blah blah. And so we have like this seat, and we have some cut here. But we can combine this guy into just one seat, right? Just one seat, big seat. We just combine to one seat with the same, some cut along A. And so the way we proceed is like this. So we write some field. We have some field. So this is CFT, and we have our QFT, quantum field theory, some quantum field theory we're talking about. So we have some field phi here, and the same field, right? 2 and 3 and so on. Phi is just a CFT field. CFT field. Just we write it the abstract way, and there are n such fields, right? N copy. So that we can just collect all of them into one seat, right? So we can just pretend all fields are on the same seat. And the only thing we have to do is we have to impose is just a boundary condition. If we go around, A, then what happens? Phi I field goes to phi I plus 1, right? The reason is simply because if we go around, then we go to second seat, right? Phi 1 now becomes phi 2, right? So we just impose this boundary condition. So this is twisted boundary condition, twisted boundary condition. condition. BC, boundary condition. And then actually you can regard this, you can think this is equivalent to the calculation of twist operator, which is like this. Let's call this position A and B. This is called twist. So now here I had in mind already now CFT. In CFT, and when we talk about twisted boundary condition like this, there are some, we can regard this twisted boundary condition as some operator, non-local operator, which we can put here, which gives this is related to twist operator. So once we put twist operator, we suddenly changes boundary condition. And this is quite well studied. This actually appears in the theory of orbifolds. Orbifold is a basic way to construct new conformal field theory description. And in orbifold theory, there are some twisted sector called twisted sector, and this twist operator belongs to that. And the orbifold means we identify like this way. So we identify phi 1 to phi 2, right? So this kind of identification. And this is and twisted sector for this identification is twist operator. Gives twist operator. And this is actually very convenient. I will come back to this later. These are my very fast summary, very quick summary of replica calculation. Now we go to a basic property of entanglement entropy called area law. So anyway, yeah, we can calculate the entanglement entropy like this way, for example, like this way or this way. But anyway, we can always find basic property called area law. For reference and so on, I write it reference in the lecture note, which I will post on the Slack. So please refer to that. For dimension, for d-dimensional quantum field theory, let's focus on vacuum state. Usually in high energy, we talk about vacuum state. But you can actually, you can think actually, finite energy state is also fine. Finite energy excitation, excited state. Applicable. For example, finite temperature state also satisfy this. But anyway, let's assume d-dimensional quantum field theory. So that means one time and d minus one space. Then entanglement entropy always behaves the following way. So this is some constant, and it's like actually entanglement entropy measures the degree of freedom, right? Number of spins, right? For example, related to number of spins, and that means this gets divergent because we are talking about continuum limits, so infinitely many spins appeared in the theory. So this is area. I will explain more details. And epsilon is this lattice constant which I introduced, and some corrections, which is higher order correction. And this leading term is called area law. Area law or area law divergence because it's divergent. And gamma is some constant, theory dependent constant. It's actually gamma is proportional to a degree of freedom, number of fields. So. Number of fields, quantum fields. Okay, and so what I had in mind is we have this setup, basic setup of entropy. This is a subsystem A, and we have a complement P, and we talk about the entanglement entropy in this region. Right? We are talking entanglement entropy in this region, and then boundary A, this one is just this boundary, right? Boundary A is this guy, right? And the entanglement entropy is proportional to the area of this boundary of A. And because the entropy is dimensionless, this is dimensionless, so we have to divide by some, length dependent, dimensionful quantity, which is actually cutoff scale. And this is heuristically, you can understand this is not so surprising because originally, how entanglement works, right? Because anyway, we are talking about ground state of some quantum field theory. You can imagine also more simple system like Ising model, right? Ising model has a nearest neighbor interaction. And because of nearest neighbor interaction, we have some entanglement, nearest neighbor sides. There are also long range entanglement, but the entanglement gets very large if we talk about nearest neighbor, right? This is entangled. These are quite dominant, And we can also have an entanglement here, but this does not, this short range entanglement don't contribute to SA, right? Because it's just inside A. Point is that entanglement with A and B, right? So that only comes from this short range entanglement like this, which is really concentrated on the boundary of A. So this is our basic heuristic origin of this area. But actually, area law is also at the same time a little bit surprising if we think about more generic state, right? So if we talk about random state, in quantum minimal system, this case actually we don't get to area law, but in general we get the volume law. This is quite well known fact. This is also related to page curve, right? How the page curve are here. It's always, generic state. You can imagine some excited state. You can very lots of spins, and you can talk about some energy scale, and there are lots of states, right? And the area law only appears in the lowest energy state. And if we talk about this kind of generic high energy state, we get volume law. But not surprising also again, because in generic state, everywhere is entangled, right? Everywhere is entangled. This point is entangled, or this point is entangled, everywhere entangled. So that case, of course, we get the volume. So area law is very special property of quantum field theory. So quantum field theory is very special because we only have local interactions, right? Very only near, sort of not exactly, but very limited to nearest neighbor-like interactions. If we talk about non-local quantum field theory, we, in general, ground state also gives some volume law entanglement, but in high energy theory, we only talk about local quantum field theory, and that's the reason we get also area law. Okay, so there are some questions. How about a state with one electron in A and one outside? So what does this mean actually? So we have one state here, one electron is here and outside, then we can have some EPR pair like entanglement, log2 like entanglement. But here, in this point, I'm talking about much larger barrier of entanglement, which is a lot of UV divergence. So if there are still questions, please ask me.
Excuse me.
Yes.
Can you hear me?
Yes.
Oh, okay. It seems like this expression doesn't depend on which ground state you choose.
Oh, good. Yeah.
There can be many ground states.
But I'm talking about just not degenerate state.
Okay.
But you can think about some little bit degenerate states, but still this is true. This is still true because small degeneration, because degeneration only gives log of some finite quantity, right?
Okay.
That's very small effect. I'm talking about this UV divergent quantity.
Okay. Okay.
Mm.
Thank you.
Good. Okay. Yeah. So yeah. Anyway, if you have any question, you can ask anytime. Sorry. Also, there are some chat. Yeah, you can also talk about local excitation. And that case, you get a finite correction. Again, local excitation also gives usually a finite contribution plus some finite. And this part changes if you excite the theory. That is true. But I'm talking about, again, divergence. So this area of divergence, small excitation don't affect at all, actually. Okay. And yeah, okay. So I just quickly explained area law, and but actually, so area law only, maybe I should say that the area law only proven in particular system like free theory, Gaussian theory, like quadratic theory. That's case we have even in any dimension. Any dimension this is proven, but in general, strongly coupled field theory. What about that? Area safety answer actually explained area law. I will explain, but except area safety, there are no. I mean, so far, no direct derivation of area law. Though we think this is true. This is just one more comment. So that way, this is not rigorous theorem, I should say, in general quantum field theory. And yeah, so time is, okay. So but still have 10 minutes, roughly 10 minutes. So now I focus on, actually, so I said this is true, right? I said this area law, but there are some exceptional case where this area law is broken. Sorry, again, there are some questions. So what about if gravity is coupled, right? So when gravity couples, there are extra term appears. So there are some Newton constants. So we have like, if we talk about gravity, so then we have, this is actually related to holographic entanglement entropy. So we talk about, like A. So we actually, this area of boundary of A, right here, is actually gives contribution. This is a Newton constant, and there are some finite contribution and plus area of divergence, which is d minus 1, d minus 2 maybe. I highlighted d minus 2, right? D minus 2 and the area. If we just literally calculate, using replica trick, we get this, 2 terms, right? But you can actually combine this into one, right? You can regard as a kind of renormalized Newton constant, like this way, because this is a bare Newton constant, and it's renormalized, right? So this bare renormalized bare Newton constant plus, this is usual renormalization procedure. This is bare, and this is also divergent, right? So we combine this into finite renormalized Newton constant. Once you do that, you get standard kind of Bekenstein-Hawking like, but not Bekenstein-Hawking, because this is not black hole, right? It's just a kind of boundary, artificial boundary, which you put. But anyway, you get this area law form. And this will become finite. And this is exactly, if we think this in area safety anti-Doshita space, this is holographic entanglement. Okay. Does this answer question? Okay. Let me go on. So yeah, so I said this area law is always true, but there are exceptions. And this famous exception is two-dimensional conformal field theory. It's a very basic example. But this doesn't say anything bad, actually. This is very natural violation. And so when we talk about, let's consider, and this is subsystem is here. And then we have like, yeah, it's a complement is B, right? And in this setup, and 2D, right? 2D means one time, and one space, right? But the time is Euclidean time. T is Lorentzian time, but tau means what I mean is Euclidean time. So I write it always. So this is the x direction, and this is time direction. Let's focus on entanglement as tau equals 0. Then entanglement entropy. Okay. So there is a very basic formula. Tells us SA equals 3 over C and log of L over epsilon. And C is central charge. And the point is that this guy is logarithmically divergent. It's logarithmically. This is something missing here. Right? Maybe you can think actually. So it's not. Sorry, it's not here. So you can think, if d equal, actually this is correspond to d equal 2 limit, right? Maybe this goes to 0, but maybe sometime you get log. And indeed, that is the reason why you get log. But naively, we just set this is 1, just constant, right? So that case, this formula contradicts with area law. Okay, and but anyway, this is a kind of small, some subtle issue of limit. So actually not a violation, I should say. But actually this formula is very, very important. So that's the reason I want to pick up this example. And but before that, maybe it is good to derive this, right? Derive this one and derive. So I'm assuming some basic knowledge of, conformal field theory. So trace law n. This is something we just explained, replicatoric. And this Zn looks like twist operator, A and B. This called this A and B. And bar means complex quantity here. And this is just R2, right? This is R2. Okay? And then this guy, actually the knowledge which we want to use, actually conformal dimension of this twist operator is known. And this is something we can derive many different ways. But we always take the central charge, related central charge. N is a replica number, right? N is replica, n minus 1 over n, and C divided by 12. So I'm using this. And then the n equal to, looks like, because there's 2-point function. Of course, L length is B minus A, right? L is this length. This length. This L. This L. This L. This L. And the 2 times delta n. And delta n is this conformal dimension. This one, right? And then, so we can write this is actually L to the C over 6, n minus 1 over n, right? And then entanglement entropy, but it is good to write it full expression for linear entropy, 1 minus n and log Cn, d1 to the nth. This is like 6 over C, 1 plus 1 over n, and log L over epsilon, right? Sorry, let me write it clearly. And of course, if we take n equal 1 limit, we produce 3 over C formula. And just we produce this. But for n, actually, it is good to note that actually there are n dependence here. Yeah. So the n dependence means if there are no n dependence, usually such a state is maximally entangled. Right, just flat space. We call it flat spectrum, right? Entanglement spectrum. Eigenvalue of reduced density matrix is just the same value, proportional to identity matrix. But n dependence means this is it has a more sophisticated structure. Okay, finally, let me make several comments of this formula. Comment. first point is yeah, what about area? No? So for massive case, for massive 2D two-dimensional quantum field theory, we have, so it's massive, so no longer conformal. But in that case, we have SA, so the entanglement entropy scales like this way. SA looks like S3 over C. They're the same, but it's logarithmic, but M over epsilon. And when L is much greater than 1 over N, which is namely correlation length, right? This is the precise correlation length, So this case, actually, we say the area law is satisfied. This case is the area law is satisfied. So the reason is that, so it's just proportional to the area, right? Area, even though we don't care about some of the cutoff scale, but they just talk about, area. Area, if we talk about region A is here, area, usually if we have higher dimension, like, 2 plus 1 dimension, we can say area is just this boundary length, right? This area, because area is del A. But this case, del A is just a point, right? We just, area is equal to point. In this case, area equals number of points of boundary. So there's a 2, right? So and if you have just 1, then we have a coefficient to become 6 over C, and that way it's just now it's proportional to the number. But previously, our previous formula does not satisfy area law because it's like proportional to log L, right? Log L. It's not area. This is the usual how especially condensed matter or statistical mechanics people says this formula is violated for 2D CFT, but satisfied for massive 2D conformal field theory, quantum field theory. Okay, and this is just kind of comments, but more practical useful comment is like following one. This is actually how entanglement entropy appears in quantum manifold system first. Historically, originally, entanglement entropies were introduced to understand actually black hole entropy. This is first done by Bombelli and Sredoniki and collaborators, and in this first paper where they discovered area law. That's the first starting point. It's quite long ago, but later, but at that time, it's not situation not so successful because the entanglement entropy is UV divergent, right? A divergent black hole entropy is finite. So how do these two guys are related, right? And also I just related to the previous question, right? I explained this, right? So I explained here, but it's like this is UV, this is entanglement entropy. But there are some extra contribution, which is peculiarity of gravity, right? So black hole entropies mainly come from this one. So this guy is not related, right? So that way it's not completely successful, but so people forgot entanglement for a while. And after that, this famous paper by Strominger and Buffer comes, and the black hole entropy is explained by D-branes, and that leads to ADS50. But that way, maybe people think the entanglement entropy is not so useful, right? That time. But after that, maybe 2005 or so, or maybe 2004, or a little bit earlier, 2000, then people realize, condensed matter people realize entanglement entropy is very useful, right? And a more simple way of saying this entanglement entropy is somehow quantum order parameter, right? Entanglement entropy is kind of nice quantum order. And so you can use also quantumizing spin chain and detect entanglement, because entanglement entropy gets divergent at the critical point. Also, you can generalize the situation to topological phases. In that case, right, there are no local quantity which characterize topological phase, but entanglement entropy can detect topological phase called topological entanglement entropy. And but even before that, the reason people notice entanglement useful use of entanglement is actually more practical numerical calculations. So here I just would like to comment. So this is something in the end we have this, but when we have in mind numerical calculation. Some complicated Hamiltonian, which we cannot exactly solve, right? So let's assume the theory is not exactly. So in that case, we have to do some numerics. And that case, people notice that this entanglement entropy is somehow log of, so von Neumann entropy, right? But the von Neumann entropy means that, roughly speaking, log of effective rank, rank size, rank of row A, right? Right. So to have some, better quality of quantum numerical calculations, we have to prepare some particular size of matrix, and this is actually given by entanglement entropy, right? So so this is something we should prepare, right? For numerical, we should prepare. This size of matrix. So the kind of estimation, how much the numerical calculation costs, right? Data resource and so on. And so this is actually original reason people start to think about entanglement, especially condensed matter people start to think about entanglement. But we know also, right? So numerical calculation very hard nearby a quantum phase transition point, right? So that these two issues is of course equivalent. And so you can, for example, estimate this, right? And for example, like C equal 1 CFT is log L, right? And to C equal 1, for example, Heisenberg spin chain. C equal 1/2, for example, Eisen. But it's 1/3, it's like Heisenberg. And this case, you can assume maybe 100 spin chains may be enough to calculate, right? So we want some 100 size. That looks like, right, quite a good number. And that case, the size, right, rank of row A looks like, it's like log to the 1/3, right? And this actually, you can like this 4.6 equivalent. It's not big actually, right? It's small actually, not large. So this means that numerical calculation of spin chain is very easy, right, using computer. But in higher dimension, if you go higher dimension, CFTs, then entanglement entropy scales like area row, right? Not logarithmic, like this. And then this rank of row A is exponential, right? This is very huge. This is we don't need to even plug this value, it's obvious this is huge. This means, in higher dimension, for example, critical point, it's very difficult to numerical calculation. Yeah? So this is, so different situation. This is spin chain. This is spin chain. That means D equal to higher dimension, D greater than 2. Right? It might be including 3. So this situation is so different. So in this, like numerical subject, numerical calculation of this condensed matter system, it's a higher dimension is always kind of frontier. It's like non-trivial, very non-trivial to do this. Okay. Okay, so I think it's already over time. So I think I will stop here. This first lecture I've done, and next I'll move on to holographic entanglement entropy.